through a decision tree algorithm. We'd like to thank our mentor, Janning, for just being there whenever we needed it and providing a lot of useful insight and help. This is our team. I'll start off. Hi, everyone. My name is Pranav, and I'm a rising junior from Dublin High, California. I enjoy math, coding, and playing piano. I signed up for the DIA internship program because I was really interested in data science. And thanks to them, I've been able to understand data analytics at like such a deep and like at such a deep level. And thanks to their speaker series, I've been exposed to like a bunch of different fields. And overall, this has really helped my interest in data science.
Hello everyone, my name is Sudarshan Gopalakrishnan and I am an incoming junior in the Bay Area at the Quaterlane School. I absolutely love coding and 3D printing, and because of DIA, I was able to gain a lot of experience with Python data science and machine learning, especially with decision tree algorithms and all of that, because this is the first time I've actually used a decision tree algorithm. So it's a very interesting summer, and I think I learned a lot from there.
Hello, my name is Susan Shen. I'm a rising senior from Rosemead High School, and besides computer science, I like learning instruments. I really want to thank DIA because it gave me an insight into data science and visualization with data. I wouldn't be able to do this without the boot camp, and I learned a lot throughout this summer.
Hello, my name is Bhuvanesh Prabhakar. I'm a rising senior from Bridgewater Raritan High School in New Jersey. I enjoy economics, and I wanted to see how that had to do with data science. So with the tools given to me by the DIA research program, I think I'll be able to sort of see the connections between economics and data science going forward. And I also really treasure the opportunity to be able to conduct research in an official manner through this research program.
So we want to start with a background on our topic and just basically the premise on which we conducted our research. So what is climate change and what is its relevance in society? As you all know, the temperature of the Earth is rapidly increasing thanks to fossil fuel emissions and other artificial changes that humans are doing to the environment. And if we don't do something about it, it poses a great threat to humanity and civilization in general, along to all life on Earth, really, because the rising temperature just means that Earth will soon become inhabitable. We see efforts to kind of mitigate it, like the Paris 2050 climate agreement, which basically says that all countries should switch to sustainable energy by 2050 if we want to mitigate climate change before it becomes irreversible. So the specific issue that we were looking for is the worsening climate and the rising land temperature. So we want to define a distinct correlation between these two so then we can inform people on what to focus and mitigate, and therefore show that climate change is not, insurmountable, but rather little by little we can all play our part in mitigating it, and therefore we can reduce climate anxiety. For data sets, we found daily air concentrations of carbon monoxide, lead, nitrogen dioxide, ozone, and sulfur dioxide. And we accessed this from the United States Environmental Protection Agency databases. And we also got a data set from meteostat.net which had daily temperature, humidity, wind speed, and other climate data like precipitation and yeah. So cleaning the data, we found when cleaning the data, we found that there was a column for snow and wind direction. There were two columns for snow and wind direction, and those had like almost all null values. So we decided to drop those. And also in the air quality data set, there was a there were some columns that we didn't need, like coordinates of the location, or the column that was like it's the general area instead of the specific city that it was in. So basically, by dropping columns and changing the name so that it was readable, filling null values, we were able to create a comprehensive data frame with all the values that we need.
These are our visualizations. We wanted to see the correlation between humidity, pressure, and wind speed with temperature and predict how our model will act with the data we trained it with. We took the data from a data set called historical hourly weather data. The slope of the line of best fit is 4.315, so the average temperature has been increasing steadily over time. The graph showed that the humidity and temperature had a negative correlation, meaning that the higher humidity would cause a lower temperature. Most of the data is skewed to the right of the graph. There is a very large range of temperatures, but if we generalize it, we can see that the greater the temperature, the higher the greater the pressure, the higher the temperature. The trend in this graph cannot be generalized, as it seems that the wind speed did not have a great effect on the temperature. And according to the graphs, humidity seems to have the most impact on temperature, as there is a strong correlation between the two factors.
All right, so now we will move to our decision tree machine learning algorithm. So how does a machine learning algorithm help us solve a problem? So first, it helps establish a clear trend. It helps establish the assertion that climate change is only going to get worse if we do absolutely nothing about it. And also it allows us to predict values too. So how did we split our data into training, validation, and test sets? So we, of course, use the scikit-learn library from Python to implement the train test split method. And also we split the data so that 70% of it is training data, 10% is validation, and 20% is testing. So how do we construct our algorithm? So this is actually a code snippet that we got. This is specifically for the training and test set. So here's the train test split function over there. CLF, which stands for classifier, that's our decision tree classifier. And we actually, as we tested out, we got a high accuracy with a max depth of 6. Because if we do, like a really high max depth, then it would do a lot of overfitting and all that, which is what we don't want. And then, yeah, of course, we fit our X train and Y train, and then we predicted X train and then also accuracy. So we actually, our decision tree was very big. And it was very hard to put in one slide. So we actually put it into 4 slides. It's very big, it's very wide. So this is the first one, second one, third one, and the fourth one. So technically that was 1 slide, but it was really 4 slides. All right, so how well did our model perform? So we put the classification reporter and the confusion matrix side by side. So essentially what happened here was so we got a much better precision and recall and also accuracy than last time, for sure. So the accuracy was 0.62. And we got pretty good precision and recall values. And if you can see in the confusion matrix, there's a lot of numbers there, but essentially out of the 6,467 predictions, our model predicted 4,016 of them correctly. So that's again displayed by the 62% accuracy of our model. And we also put the pressure, I mean the F1 score and all that as well.
All right. So using the predict function, we individually tested to see if the maximum values of humidity, pressure, and wind speed would have the most effect on the temperature. So seeing which feature had the greatest effect. So the default values for prediction were the means of all three of the used feature columns. So we calculated the means as seen on the left. And from the output, humidity and wind speed did not result in a change of labels, whereas pressure did. And so conclusions, the only conclusion we can really draw is that there is a correlation between a continued rise in the average daily temperatures in LA and the continued increase of humidity, decrease in wind speed, and increase in pressure, but it's mostly prevalent with pressure. So did we solve our problem? While we were able to draw a distinct correlation between the increase in features we were analyzing and the rise in average daily temperatures in LA, our problem still remains unsolved because the limited nature of our model did not let us ascribe causality between the rise in features and the rise in average daily temperatures. So we can't really motivate any substantial action from this reliably. The usefulness of our research is to motivate further, more in-depth studies into the climate and the temperature of various areas globally that can alleviate climate anxiety through causing greater change. So these are some relevant further reading and research. So we have the first articles on climate anxiety, and then the second and third are on general facts about climate change. Thank you so much for listening. Are there any questions?
Thank you for this awesome presentation. Yeah, let's open the ground for questions from the audience, if any.
So I had a question. I saw that you had a decision tree that spanned across 4 slides. So what was at the root node of your decision tree? What was the deciding feature, if you can call it? And what conclusions did you draw about how that affected the outcome?
Yeah, so this also related to the thresholds that we used, as we described in our previous presentation last week, so for the temperature. But before I get into that, the feature columns that we used were humidity, pressure, and wind speed, of course. But the temperature label, so instead of actually doing like a 0 and 1, it is 0 and 1 to classify temperature, we actually used 3 labels, low, medium, and high, to represent low temperature, medium temperature, and high temperature respectively. So what we did there, in order to actually classify it as low, medium, or high, what we did was, if the temperature, for example, if it's within the interquartile range, then it will be classified as the medium temperature. If it's lower than the first quartile value, then it would be classified as low temperature. And if it's if it's higher than the third quartile value, then it would be classified as high temperature. So in the very bottom row here, you can see all the labels like low, medium, and high. So that's what was used in the decision tree.
Yeah.
If I may, I have.
Okay. Yeah, go ahead.
Yeah, I was going to ask. I probably missed it, but what is the range of the time range across which your data spanned? Like, is it a few years or is it
1980 to 2020?
20 years.
Okay. Yeah, but so that's like the data we found, like overall. But the data that we used was actually from just 2012 to 2017, but it was actually hourly data. So that's why we had lots of data. It was actually because it was hourly data for 5 years. It was we got a lot of data, around 40,200, something like that. I don't know the exact number, but around that. It's a very big number.
Yeah, thank you.
Yeah, I have a question here. So I assume you had the data from EPA and greenhouse gas emissions. Did you get a chance to look at the correlation between the greenhouse gas emissions and the temperature?
Not exactly the greenhouse gas emissions themselves, but basically we wanted to see what. So, well, the pressure, humidity, and wind speed, and all of those kinds of features are definitely causing the greenhouse gases themselves. We wanted to see which of those features has, like the most impact on the temperature. So then we know what to do in order to at least, slow down the increase of global warming in the world.
Yeah, so a more focused study that looks at maybe the most recent climate documents released, and as well as the correlation between greenhouse gas emissions and the rise in temperatures is something that can motivate further study for sure.
Right. Yeah, just another follow-up question. Do you think the temperature causes the humidity changes, or the other way around?
I mean, as we said in the slides, we can't say either way from just the study that we have conducted because we can't ascribe causality. However, we are going to say that it is, at least from what I know, I can't substantiate this claim using the data, but from what I know about how the environment works, I'd say it's a little bit of a feedback loop. So they both like cause each other. So an increase in one causes an increase in the other, which causes an increase in the other when referring to climate change and greenhouse gas emissions. However, that's not something we could substantiate with the data that we currently have.
Thank you. Nice presentation.
Thank you.
Thank you. Thanks for the team that just presented. That is awesome. And I think this is a good opportunity for us to pause. The